July 15th, 1945, Freeman Field, Indiana. American engineers circle what appears to be a missile with a cockpit bolted on top. No propeller. Wings smaller than a Piper Cub's. A fuselage fat as a torpedo sitting on a wooden skid. This is the Messerschmitt Me 163 Komet, Nazi Germany's most advanced fighter aircraft, the world's first operational rocket-powered interceptor, 623 miles per hour in level flight, 0 to 39,000 feet in 3.5 minutes, faster than anything the Allies have ever built. The German wonder weapon that was supposed to sweep Allied bombers from European skies. But as Colonel Harold Watson's technical team begins their examination, the first warning labels appear: German text requiring immediate translation, emergency shower heads mounted near fuel tanks, missing landing gear replaced by a single retractable skid. Flight logs from the Luftwaffe's Jagdgeschwader 400 tell a different story than the propaganda. Aircraft written off, fuel incident, pilot hospitalized, chemical burns, landing accident, aircraft destroyed, pilot deceased. The revolutionary fighter that promised to change aerial warfare forever had one small problem. It was killing more German pilots than Allied bombers. The summer heat at Freeman Field created shimmering mirages across the Indiana tarmac, but nothing could distract from the bizarre aircraft that had arrived 3 weeks earlier aboard a C-54 cargo plane. FE 500, serial number 1913A1, represented everything American aviation engineers thought they understood about fighter aircraft design and violated every principle simultaneously. Major Gustav Lundquist approached the Messerschmitt Me 163 with the methodical precision that had kept him alive through 18 months of experimental aircraft testing. The Komet's proportions defied logic. Where American fighters stretched sleek and purposeful, this German machine hunched like a pregnant bullet. The wings, if they could be called wings, appeared comically small, barely wider than those on training gliders he'd flown as a cadet. The entire aircraft measured only 19 feet from nose to tail, yet weighed nearly 9,000 pounds when loaded. Colonel Watson wants a complete technical assessment before we attempt any flight operations, Lundquist told the team of Wright Field engineers gathering around the aircraft. They moved with the careful reverence reserved for unexploded ordnance, which, given what they'd learned about the Komet's fuel system, wasn't entirely inappropriate. Dr. James Morrison, the team's propulsion specialist, circled the aircraft's rear section where the Walter rocket motor sat like a metallic tumor. "No external air intakes," he muttered, taking notes. "The entire propulsion system operates independently of atmospheric oxygen. Completely self-contained chemical reaction." He paused at a series of German warning labels plastered around what appeared to be fuel access panels. These markings, they're not standard Luftwaffe maintenance instructions. Technical Sergeant Bill Hayes, fluent in German from 2 years as a prisoner of war, leaned closer to translate. His face went pale. "Lebensgefahr," he read slowly. "Mortal danger. Do not approach without protective equipment. Emergency decontamination required after fuel handling." He looked up at the other engineers. There are similar warnings around both fuel systems. Different chemicals, different procedures. They're treating this thing like it's radioactive. The landing gear presented another mystery that challenged fundamental aviation principles. Instead of the robust tricycle arrangement found on modern American fighters, or even the conventional tailwheel configuration of older designs, the Komet sat on a single retractable skid mounted centerline beneath the fuselage. 2 small outrigger wheels, barely larger than bicycle tires, prevented wingtip strikes during ground handling. "How does it land?" asked Lieutenant Robert Chen, the structural analysis specialist. "A 9,000-pound aircraft hitting the ground at landing speed on a single skid? The deceleration forces would be enormous." Lundquist examined the skid mechanism more closely. The German engineering was typically precise: multiple shock absorbers, reinforced mounting points, even a small drogue parachute compartment in the tail section. "They've obviously thought about it," he said, "but thinking about a problem and solving it aren't the same thing." The cockpit revealed the Komet's most human element, and perhaps its most troubling. The pilot's seat, cramped even by fighter standards, was surrounded by instruments labeled in Gothic German script. But it was what wasn't there that caught Lundquist's attention. No provisions for extended flight. No navigation equipment beyond basic compass and altimeter. The fuel quantity gauges showed dual systems with alarmingly small capacity numbers. 8 minutes, Morrison announced from his examination of the fuel system documentation. Maximum powered flight duration is 8 minutes. After that, he gestured toward the small wings. Glider. The implications began settling over the engineering team like a slowly descending fog. This wasn't a fighter aircraft in any conventional sense. It was a manned missile with just enough control authority to aim itself at enemy bombers before becoming a powerless gliding target for Allied escort fighters. Hayes continued translating captured German technical manuals, his voice growing increasingly incredulous. Fuel handling procedures require separate trucks for each chemical system. The trucks must maintain 800 meters separation during transport. Ground crews need specialized protective suits. Emergency decontamination showers are mandatory at every operational base. He paused. Listen to this. Under no circumstances should T-Stoff and C-Stoff be allowed to mix outside the combustion chamber. Immediate explosion and toxic gas generation will result. The fuel chemistry lesson came courtesy of Dr. Sarah Kellerman, the team's chemical warfare specialist who'd been analyzing samples of the Komet's propellants captured at German airfields. T-Stoff is concentrated hydrogen peroxide, 80% purity, she explained, her tone carrying the flat precision of someone who'd seen too many chemical accidents. It's not just an oxidizer. In concentrations above 50%, hydrogen peroxide becomes a contact poison. Dissolves organic matter on contact, including human tissue. She held up a second sample container. C-Stoff is the fuel component. Methanol, hydrazine hydrate, and water. The hydrazine makes it hypergolic, ignites spontaneously when it contacts the T-Stoff. But hydrazine is also a potent neurotoxin and suspected carcinogen. The Germans essentially built a fighter aircraft powered by industrial poison. The mathematics of the Komet's operational profile painted an even grimmer picture. Lundquist worked through the numbers with Morrison and Chen, using performance figures extracted from captured Luftwaffe documents. Maximum speed, 623 miles per hour. Service ceiling, 39,000 feet. But these impressive figures came with deadly caveats. Approach speed for aerial combat, Lundquist calculated, would be over 500 miles per hour. Even if the pilot achieves perfect position behind an enemy bomber formation, he's got maybe 3 seconds in the firing solution before he overshoots. 3 seconds to line up, acquire target, and fire. He looked up from his slide rule, and that assumes the bomber crews don't take evasive action. The ammunition capacity provided another sobering revelation. The Komet carried two 30mm Mk108 cannons with 60 rounds per gun. In the brief moment available for aerial combat, a pilot might fire 2 or 3 short bursts before exhausting his ammunition completely. After that, he'd be flying a defenseless glider while Allied escort fighters converged on his position. The tactical doctrine makes no sense, Chen observed. You've got an aircraft that requires perfect weather, perfect maintenance, perfect fuel handling, perfect piloting technique, and perfect timing, all simultaneously. No military system can sustain those requirements operationally. As afternoon shadows stretched across Freeman Field, the American engineering team began compiling their preliminary assessment. The Messerschmitt Me 163 represented genuine technological innovation married to operational suicide. Revolutionary performance characteristics undermined by fundamental design compromises that prioritized speed over survivability, firepower over sustainability, and theoretical capability over practical effectiveness. The wonder weapon that was supposed to revolutionize aerial warfare had instead become a monument to the principle that advanced technology without operational wisdom produces expensive failure. And somewhere in the captured German files, the casualty reports waited to confirm what American engineers were already beginning to suspect. The Komet had killed more of its own pilots than it had killed Allied airmen. The chemistry laboratory at Wright-Patterson Army Airfield had seen its share of dangerous experiments, but nothing quite prepared Dr. Sarah Kellerman's team for the controlled terror of working with German rocket fuels. Through the autumn of 1945, they conducted systematic tests with captured samples of T-Stoff and C-Stoff, building what would become the definitive American understanding of hypergolic propellant systems. T-Stoff arrived in specially marked containers that German ground crews had abandoned at Brandes Airfield during the final weeks of the war. The clear liquid appeared innocuous until Kellerman's first demonstration. She placed a small piece of raw beef into a glass beaker, then added a few drops of the 80% hydrogen peroxide solution. The meat began dissolving immediately, bubbling and frothing as the concentrated oxidizer broke down organic compounds at the molecular level. "This is what happens to human tissue on contact," she explained to the gathered engineers, her voice carrying the clinical detachment of a pathologist. The German technical manual states that T-Stoff exposure requires immediate flooding with water, followed by medical treatment for chemical burns. But at 80% concentration, there may not be time for treatment. The second demonstration proved even more sobering. C-Stoff, the fuel component, contained methanol for combustibility, hydrazine hydrate as a catalyst, and water as a stabilizer. When Kellerman mixed drops of each propellant in a separate container, the result was immediate and violent, a bright orange flame accompanied by toxic vapor that triggered the laboratory's ventilation alarms. "Hypergolic ignition," she announced as technicians cleared the air with powerful fans. "No spark required, no ignition delay. The moment these chemicals contact each other, you get spontaneous combustion at temperatures exceeding 3,000 degrees Fahrenheit." She gestured toward the scorch marks on the laboratory table. Now imagine that reaction occurring inside a rocket combustion chamber, generating thrust equivalent to 4,000 horsepower. Major Lundquist studied the captured German technical documentation with growing incredulity. The fuel loading procedures read like instructions for handling plague samples. T-Stoff required specialized trucks with explosion-proof electrical systems. C-Stoff traveled in separate vehicles that maintained minimum 800-meter separation from T-Stoff transports. Ground crews wore full protective suits during fuel handling, and emergency decontamination showers were mandatory equipment at every operational base. The human element became starkly clear when Technical Sergeant Hayes translated casualty reports from Jagdgeschwader 400, the Luftwaffe's operational Komet unit. The files contained meticulous German record-keeping that documented every incident, injury, and fatality associated with the Me 163 program. December 30th, 1943, Hayes read from a Luftwaffe incident report. Oberleutnant Josef Pues, test pilot, Bad Zwischenahn airfield. Aircraft suffered hydraulic failure during takeoff. Jettisoned, dolly bounced higher than calculated, struck ventral fuel line, emergency landing attempted. Hayes paused, his face grim. Aircraft inverted on touchdown, pilot trapped in cockpit, T-Stoff leak resulted in a complete dissolution of organic matter. The report continued with clinical German precision that somehow made the horror worse. When rescue crews reached the inverted aircraft, They found Puss had been chemically dissolved alive while trapped unconscious in his harness. The concentrated hydrogen peroxide had eaten through flesh, bone, and fabric with equal efficiency, leaving only his metal dog tags and portions of his flight suit's leather components. The rescue crew required hospitalization for chemical exposure, Hayes finished. 3 ground personnel suffered severe burns just from approaching the wreckage. Dr. Kellerman's chemical analysis explained the lethality with brutal clarity. Concentrated hydrogen peroxide didn't just burn, it catalyzed the rapid decomposition of organic compounds, breaking down proteins and cellular structures through oxidative processes that continued until the chemical was diluted or exhausted. In a confined space like an aircraft cockpit, even a small leak could prove fatal within minutes. The operational mathematics proved equally devastating. Each Me 163 carried 1,040 liters of T-Stoff and 492 liters of C-Stoff. The Walter rocket motor consumed these propellants at a rate of 150 liters per minute, providing a maximum powered flight duration of 7 minutes and 30 seconds under ideal conditions. Pilots who attempted extended high-power climbs could exhaust their fuel in as little as 4 minutes. Major Lundquist worked through the tactical implications with Morrison and Chen, using performance data extracted from captured test reports. The pilot has to execute a perfect intercept, he explained, drawing diagrams on the laboratory blackboard. Rocket-powered climb to bomber altitude, brief engagement window, then immediate gliding descent to base. No second chances, no extended combat, no margin for error. The maintenance requirements compounded the operational nightmare. After each flight, regardless of whether the pilot had fired the rocket motor, the entire fuel system required complete flushing with distilled water. Residual T-Stoff and C-Stoff could not be allowed to remain in fuel lines, pumps, or injectors, where they might spontaneously react during subsequent operations. This decontamination process took ground crews 4 to 6 hours per aircraft. Morrison discovered additional complications in the German engineering manuals. The Walter rocket motor generated exhaust temperatures that exceeded the melting point of steel. Special ceramic throat inserts provided thermal protection, but these components cracked frequently and required replacement after every few flights. The rocket nozzle itself suffered thermal erosion that degraded performance incrementally, meaning thrust calculations were valid only for engines with fresh components. The logistics are impossible, Chen concluded after reviewing supply requirements. Each operational sortie requires specialized fuels that can't be stored together, ceramic components that crack under normal use, protective equipment for ground crews, and decontamination procedures that take longer than the actual flight. He gestured toward the stack of German technical manuals. They built an aircraft that needs industrial infrastructure just to put one pilot in the air for 8 minutes. The captured incident reports revealed the human cost of these engineering compromises. Beyond Puss's gruesome death, the files documented numerous cases of pilots hospitalized for chemical burns, ground crew fatalities from fuel handling accidents, and aircraft destroyed by spontaneous propellant reactions during maintenance procedures. The wonder weapon that promised revolutionary performance delivered revolutionary casualties to its own side. As winter settled over Wright-Patterson, the American engineering team compiled their assessment of the Komet's fuel system. The Hypergolic propellants provided unprecedented performance, but at a cost measured in pilot lives rather than strategic effectiveness. The chemistry that enabled the world's fastest fighter aircraft also made it the world's most dangerous aircraft to operate. German engineering brilliance had created a tactical weapon that was literally too toxic to use effectively, too dangerous to maintain reliably, and too lethal to its own crews to justify operationally. The captured records from Jagdgeschwader 400 arrived at Wright-Patterson in February 1946 aboard a military transport carrying the final batch of German aviation documents. Major Wolfgang Spate's meticulous unit records, preserved through the chaos of Germany's collapse, provided American intelligence officers with an unprecedented view into the operational reality of rocket-powered fighter combat. Captain Robert Sterling, chief of the Foreign Aircraft Analysis Division, spread the translated documents across his desk, like a coroner examining evidence. The numbers told a story that contradicted every piece of German propaganda about the Komet's revolutionary effectiveness. From July 1944 through May 1945, JG-400 had attempted approximately 300 combat sorties. Against this massive commitment of resources and pilot lives, they had achieved 16 confirmed Allied aircraft destroyed. 16, Sterling announced to the assembled intelligence team. In 11 months of operations, using the most advanced fighter aircraft in the German inventory, they shot down 16 Allied bombers and fighters. He paused, letting the implication settle. Their own casualties during the same period, 23 pilots killed in combat and training accidents, plus an unknown number of ground personnel lost to fuel handling incidents. The tactical failure emerged clearly from Spate's combat reports. Me-163 pilots faced an impossible geometry problem with lethal consequences for wrong answers. Approaching Allied bomber formations at speeds exceeding 500 miles per hour, they possessed roughly 3 seconds in the firing solution before overshooting their targets. The 30mm Mk-108 cannons carried only 60 rounds per gun, enough ammunition for perhaps 4 brief firing passes if the pilot managed perfect energy management. Lieutenant Colonel James Murphy, Sterling's tactical analyst, worked through the mathematics with slide rule precision. Average engagement window, 3.2 seconds. Average ammunition expenditure per kill, 47 rounds from both guns combined. But here's the critical factor. Allied escort fighters learned to exploit the Komet's fundamental weakness almost immediately. The weakness was brutally simple. After the Walter rocket motor exhausted its fuel supply, the Me-163 became a powerless glider with poor aerodynamic efficiency. Allied fighter pilots quickly adopted tactics that avoided engagement during the Komet's powered climb phase, instead positioning themselves to attack during the inevitable gliding descent when the German aircraft could neither accelerate nor climb to escape. Spate's own words, preserved in unit war diaries, revealed the growing desperation of Komet operations. The enemy fighters wait like vultures, he had written in March 1945. They allow us to exhaust our fuel attacking the bombers, then pounce when we are defenseless. My pilots report feeling hunted during every gliding approach to base. We have become prey in our own airspace. The maintenance crisis compounded tactical failures into operational paralysis. Sterling's team analyzed German supply records that showed T-Stoff production declining precipitously through late 1944. The specialized chemical plants required for hydrogen peroxide concentration had become priority targets for Allied bombing campaigns. By February 1945, fuel shortages grounded most Komet squadrons regardless of pilot availability or aircraft condition. Technical Sergeant Hayes translated increasingly desperate maintenance reports from German airfields. Bad Zwischenon reports T-Stoff supplies exhausted, he read, from a January 1945 signal intercept. Request immediate resupply for continuation of operations. Pilot standing by with aircraft, but no fuel available for combat sorties. The response, filed 3 weeks later, was characteristically bureaucratic. T-Stoff production suspended indefinitely due to strategic material shortages. Maintain aircraft in ready condition pending fuel availability. The human cost statistics painted an even grimmer picture when Sterling's team compiled comprehensive casualty data. Beyond combat losses, the Me-163 program had killed its own personnel through an expanding catalog of accident types. Fuel handling incidents accounted for 12 ground crew deaths. Training accidents claimed 14 pilots during conversion courses. Aircraft structural failures killed 6 more pilots during routine ferry flights and maintenance test hops. Dr. Morrison arrived from Wright-Patterson with additional technical intelligence that explained the maintenance nightmare in brutal detail. Each operational sortie requires complete fuel system decontamination, he reported. 4 to 6 hours of specialized maintenance for every 8 minutes of powered flight. Ground crews need protective equipment that costs more than a conventional fighter's armament system. And here's the critical factor. Mission-capable rates never exceeded 30%. The comparative analysis devastated any remaining illusions about Komet effectiveness. Sterling's team calculated kill ratios for major fighter aircraft types using comprehensive loss data from both sides. The North American P-51 Mustang achieved 5.8 enemy aircraft destroyed per pilot lost in combat. The Messerschmitt Bf-109, Germany's conventional fighter workhorse, managed 4.2 kills per pilot casualty. The revolutionary Me 163, with its unprecedented performance specifications and advanced technology, achieved 0.69 enemy aircraft destroyed per pilot lost. The wonder weapon killed more Germans than Americans, Sterling observed, with the flat precision of an accountant reviewing failed investments. If you include ground crew casualties from fuel incidents, the ratio becomes even worse. The Komet program represents the ultimate inversion of military effectiveness, advanced technology producing negative tactical results. The strategic implications emerged when Murphy calculated alternative resource allocations. The Me 163 program had consumed materials and manufacturing capacity equivalent to 4,000 conventional fighters. Those same resources applied to Focke-Wulf 190 or Messerschmitt Bf-109 production might have generated 2,000 additional Allied aircraft losses instead of the Komet's 16 confirmed kills. German engineering created a machine that demanded perfect conditions, Murphy concluded, perfect weather for takeoff and landing, perfect fuel handling to prevent fatal accidents, perfect tactical execution within impossible time constraints. Perfect maintenance procedures that consumed more resources than the combat results justified. He gestured toward the stacks of captured documents. No military system can succeed when it requires perfection at every level simultaneously. The final intelligence assessment, classified and distributed to senior Air Force leadership in March 1946, contained a single devastating conclusion. The Messerschmitt Me 163 represented the most expensive tactical failure in aviation history. German engineers had created an aircraft so revolutionary that it transcended conventional military utility, so advanced that it became primitive in actual combat conditions. The rocket-powered interceptor that promised to sweep Allied bombers from European skies had instead demonstrated the eternal principle that operational wisdom matters more than technological innovation, and that killing your own pilots more efficiently than enemy pilots constitutes the ultimate definition of strategic defeat. The morning of May 3, 1946, brought crystalline skies over Muroc Dry Lake, California, perfect conditions for what would become the most revealing flight test in American aviation history. FE-500 sat on the hardpan like a metallic sculpture, surrounded by technicians making final preparations for the first American evaluation flights of a captured Me 133. The irony wasn't lost on Major Lundquist. They were about to test fly the world's most advanced fighter aircraft without using its revolutionary propulsion system. Dr. Alexander Lippisch stood beside the aircraft he had designed, watching American engineers systematically prepare for powered flight tests that would never occur. The brilliant German aerodynamicist had arrived at Muroc 3 weeks earlier as part of Operation Paperclip, expecting to demonstrate his masterpiece to impressed American colleagues. Instead, he found himself witnessing the methodical dissection of everything wrong with his creation. The fuel system presents unacceptable risks for test operations, Lundquist explained to Lippisch through an interpreter. We'll conduct unpowered glide tests to evaluate basic flight characteristics. The rocket motor remains sealed and inert. He gestured toward the B-29 Superfortress positioned nearby, its tow cable already rigged for high-altitude release operations. We'll use conventional tow procedures to 35,000 feet, then evaluate gliding performance back to base. Lippisch's response, translated by Technical Sergeant Hayes, carried the frustration of genius confronting practical limitations. The Komet cannot be properly evaluated without its propulsion system, the German designer insisted. The rocket motor defines every aspect of its operational character. You are testing only half an aircraft. His engineering pride clearly bristled at the prospect of his revolutionary fighter being reduced to a simple glider. The first unpowered flight on May 7th revealed problems that had nothing to do with fuel chemistry. Lieutenant Robert Chen, monitoring structural loads from the ground, watched FE-500's wooden wing construction flex, alarmingly, during the initial tow phase. Wing delamination detected, he radioed to Lundquist in the cockpit. Recommend reducing tow speed and monitoring for separation indicators. The landing approach demonstrated the Komet's fundamental design compromise between performance and survivability. Approaching the dry lake at 125 miles per hour with no power available, Lundquist found the aircraft's glide characteristics marginal at best. The tiny wings generated insufficient lift at low speeds, creating a sink rate that required precise energy management to avoid a destructive ground impact. Touchdown was more controlled crash than conventional landing, Lundquist reported during the post-flight briefing. The single skid provides adequate ground contact, but lateral stability during rollout is problematic. Any crosswind component or uneven surface could result in aircraft loss. He paused, consulting his notes. Flight controls are hypersensitive at high speed, but become mushy near stall speed. There's no comfortable margin for pilot error. The second test flight, conducted on May 10th, focused on handling characteristics at various altitudes and configurations. Dr. Morrison accompanied the mission in a chase plane, documenting the Komet's flight behavior through high-speed photography. What he recorded challenged fundamental assumptions about advanced aircraft design. Control surface effectiveness varies dramatically with airspeed, Morrison reported. At speeds above 400 miles per hour, the aircraft exhibits dangerous control sensitivity. Small stick inputs produce violent attitude changes. Below 200 miles per hour, control authority becomes insufficient for safe maneuvering. There's essentially no speed range where the aircraft provides predictable, comfortable handling qualities. Lippisch observed these evaluations with growing dismay, watching his theoretical masterpiece fail basic operational requirements that conventional aircraft met routinely. His delta wing design, mathematically elegant and aerodynamically revolutionary, proved nearly impossible to fly safely under real-world conditions. The same characteristics that enabled unprecedented speed also created handling qualities that demanded superhuman pilot skill. The structural inspection following the second flight revealed additional concerns that further undermined confidence in the Komet's operational suitability. The wooden wing construction, necessitated by wartime material shortages, showed stress cracking around attachment points. The landing skid mechanism exhibited wear patterns suggesting premature failure under repeated operational use. Even the cockpit instrumentation proved inadequate for the aircraft's performance envelope. German engineering focused entirely on achieving maximum performance, Chen explained to the evaluation team. Every design decision prioritized speed and climb rate over pilot safety or operational reliability. They built an aircraft that performs magnificently under perfect conditions, but fails catastrophically when anything goes wrong. The tactical evaluation proved even more damning. Using captured German combat procedures, Lundquist attempted simulated bomber interception profiles during subsequent test flights. The results confirmed American intelligence assessments about the Komet's fundamental operational limitations. The intercept geometry is nearly impossible to execute successfully, he reported after flying multiple mock attack profiles against a formation of B-25 Mitchell bombers. Approach speed differential leaves approximately 2 seconds for target acquisition and weapons firing. Any evasive maneuvering by the target aircraft makes successful engagement unlikely. The pilot becomes a passenger to physics rather than an active combatant. The weapons system evaluation, conducted using camera equipment installed in place of the Mk-108 cannons, revealed additional tactical failures. The brief firing window, combined with the aircraft's hypersensitive controls, made accurate gunnery nearly impossible. Film analysis showed successful target tracking in less than 20% of simulated engagement attempts. Colonel Watson arrived at Muroc for the final evaluation flights, bringing with him the comprehensive intelligence assessment of Komet combat performance compiled at Wright-Patterson. His presence transformed the test program from technical curiosity into strategic evaluation of enemy capabilities. "We're not just testing an aircraft," Watson announced to the assembled team. "We're evaluating the German approach to revolutionary military technology. The question isn't whether the Me-163 works. We know it flies. The question is whether it works well enough to justify its enormous costs and casualties." The answer emerged clearly during Watson's own flight in FE-500 on May 21st. As an experienced test pilot and combat veteran, he possessed the skills necessary to evaluate the Komet's potential under operational conditions. His assessment, delivered with characteristic directness, demolished any lingering respect for German aviation innovation. "This aircraft represents the triumph of engineering theory over operational wisdom," Watson declared during the final briefing. "It achieves unprecedented performance through design choices that make successful combat employment nearly impossible. The Germans built a machine that asks pilots to survive their own fuel system before engaging enemy aircraft, then survive impossible tactical geometry while flying an aircraft that provides no margin for error." He gestured toward FE-500, now permanently grounded pending transfer to the Smithsonian Institution. "Revolutionary technology without practical application is just expensive failure with better publicity." The conference room at Wright-Patterson Army Airfield buzzed with an energy that Captain Robert Sterling had rarely witnessed during his 3 years analyzing captured enemy equipment. It was August 15, 1946, and the final evaluation briefing for the Me-163 program had drawn senior officers from across the Army Air Forces. What began as a technical assessment had evolved into something approaching theater, a systematic demolition of German aviation mythology conducted with slide rules and statistical analysis. Colonel Watson stood before a wall-mounted chart displaying comparative aircraft performance data, his pointer tracing lines that told the story of revolutionary technology meeting operational reality. "Mission-capable rate for the Me-163," he announced, averaged 28.4% during peak operational periods. Compare this to conventional fighters of the same era. P-51 Mustang, 86%. FW-190, 72%. BF-109, 68%. The numbers painted a picture of engineering brilliance undermined by practical impossibility. Dr. Morrison presented his chemical analysis findings with the precision of a prosecutor building a case. T-Stoff and C-Stoff require specialized handling procedures that consume more man-hours than actual flight operations, he explained. Each 8-minute combat sortie requires 4 hours of pre-flight preparation and 6 hours of post-flight decontamination. The fuel system alone requires more maintenance than an entire conventional fighter squadron. Major Lundquist's flight test assessment provided the human perspective on what statistical analysis suggested. The aircraft demands perfection from its pilot under conditions where perfection is impossible to achieve, he reported. Control sensitivity requires constant attention during high-speed flight. Energy management becomes critical with no margin for error. Landing approach characteristics eliminate any possibility of successful recovery from pilot mistakes or equipment failures. General Curtis LeMay, commanding officer of the Strategic Air Command, leaned forward in his chair as the briefing continued. His presence elevated the proceedings beyond technical curiosity into strategic assessment. The man responsible for planning America's future air operations was evaluating whether revolutionary German aviation technology posed any threat to American air superiority. Lieutenant Colonel Murphy presented the tactical analysis that would become definitive in American aviation circles. Combat effectiveness ratio for the Me-163, 0.69 enemy aircraft destroyed per pilot lost. This represents the worst performance of any operational fighter aircraft in recorded military history. He paused, allowing the implications to register. By comparison, our P-51 Mustang achieves 5.8 kills per pilot, a casualty. The Germans created a wonder weapon that was 14 times less effective than our conventional fighters. The cost-benefit analysis proved equally devastating. Sterling's economic assessment revealed that the Me-163 program had consumed resources equivalent to 4,000 conventional fighters while achieving tactical results inferior to 50 conventional aircraft operating under normal conditions. German industry allocated materials for revolutionary technology when incremental improvements to existing designs would have produced vastly superior results, he concluded. Dr. Lippisch sat silently through much of the briefing, watching American officers systematically dismantle his life's work with methodical precision. When invited to respond, his comments reflected the tragedy of genius divorced from practical wisdom. The Komet represents aerodynamic advancement beyond anything achieved previously, he insisted through Hayes's translation. Its performance characteristics remain unmatched by any aircraft in current production. Performance without survivability is suicide, not aviation, Watson replied with characteristic bluntness. Your aircraft achieves unprecedented speed by requiring its pilots to accept unprecedented risk. That's not revolutionary design, that's institutionalized pilot murder disguised as technical innovation. The moment that would be remembered decades later occurred when Major Chen presented his structural analysis findings. The wooden wing construction, necessitated by wartime material shortages, exhibited stress patterns that guaranteed structural failure under repeated operational use. The landing skid system showed wear characteristics that made successful recovery impossible after extended combat deployment. Even the rocket motor mounting points displayed metal fatigue that threatened catastrophic in-flight breakup. Gentlemen, Chen announced with the gravity of an engineer delivering a safety assessment, the Me-163 is not just operationally unsuitable, it's structurally unsound. Continued flight operations would result in inevitable aircraft loss through mechanical failure, regardless of combat effectiveness or pilot skill. The laughter began quietly, starting with a few officers who had spent months analyzing German technical claims against operational reality. It spread gradually through the briefing room as the full scope of the Komet's failures became apparent. This wasn't cruel mockery of German engineering. It was the incredulous response of professionals recognizing the ultimate technical contradiction. General LeMay's assessment, delivered with the authority of America's premier air warfare strategist, provided the official verdict that would guide American aviation development for decades. The Germans confused technological sophistication with military effectiveness, he declared. They built an aircraft that succeeded brilliantly at being revolutionary while failing, catastrophically at being useful. This represents the classic mistake of prioritizing innovation over application. The final statistics, compiled from months of analysis, revealed the Me-163's true legacy. Total program cost equivalent to 8,000 conventional fighters. Total confirmed Allied aircraft destroyed, 16. Total German personnel killed through fuel accidents, training incidents, and combat losses. 47 confirmed, with additional casualties likely unreported. The Wonder Weapon had achieved a negative kill ratio unprecedented in military aviation history. The Komet program demonstrates that advanced technology without operational wisdom produces expensive failure, Watson concluded. German engineers created a machine that required perfect conditions, perfect maintenance, perfect piloting, and perfect luck, simultaneously and repeatedly. No military system can succeed under such constraints. The briefing ended with recommendations that would influence American aerospace development through the jet age and beyond. Revolutionary technology would be pursued through systematic research programs rather than rushed combat deployment. Pilot safety would remain paramount regardless of performance advantages. Operational requirements would drive technical specifications rather than allowing technical possibilities to dictate operational doctrine. As officers filed out of the briefing room, the consensus was clear. The Messerschmitt Me 163 represented the ultimate lesson in military technology development. Brilliance without wisdom produces failure disguised as innovation. The captured Wonder Weapon had taught American aviation more through its failures than most successful programs achieved through their victories. The laughter that echoed through Wright-Patterson that August afternoon wasn't directed at German engineering skill. It was the natural response of professionals recognizing genius gone tragically wrong.